just waiting. It's working here.
Yeah.
So I'm sorry, it's going to be maybe with a bit less humor, but I'm British, so I don't know if you really want British humor. So. Okay. So good afternoon, everyone. So I'm Rachel Azulay. I work at Tetmet. I'm head of applications engineering. And basically what we do is we have developed a manufacturing tool for creating lattice structures. We're a 2.5-year-old startup from Paris. And I'm going to be talking about a tool that we developed for our process called LDS. And so, yeah, there's going to be a bit about the manufacturing and then the actual tool. So we're lucky enough to live next to one of the most famous lattice structures in the world, the Eiffel Tower. So it was actually in the first presentation of this conference, so it's quite funny. And I think it's a perfect example of civil engineering and what they have done best, which is distribute load efficiently, also have minimizing material, maximizing strength, things that we have really looked into also in terms of architectured materials. So basically what we do at Tetmet is we do the same thing, but at a smaller scale. So if we look at architectured materials, because I have a background in theoretical mechanics, so we know that performance isn't just about the material we choose, it's also to do with the geometry that we have of the material and how we arrange it. And basically, if we have a look at what's happening over there, we have an Ashby chart of material properties like yield strength versus density, and there's a huge zone of interest on the top left right there, where we know we can push some boundaries with lattice structures. And so by carefully choosing some of the properties, we can tap into this potential. We can choose stiffness, weight, crack propagation paths, you name it. And the aim is to unlock performance that comes from structure as much as it comes from the material. So how do we do this? I mean, this is basically the photo of the conference. We can tune density by changing local lattice density, either by varying strut radius or by densifying. We had a lot of shoe presentations. I didn't really know before this when I was actually, this is a slide that we usually use, but I'm glad to see that it is useful in the shoe industry. You can choose your unit cell, so different unit cells are going to have different properties. So that's also interesting. And then you can do some really funky things. You can do some thermal tuning. You can do some more like instability related properties. And so that's really tweaking up to the very edge of what you can do with lattice structures. What are the applications of all of this? So having done a PhD in this and coming from academia, the question is always, why are we doing this? What's it for? There's use in lightweighting, obviously, because we create less dense structures. So any transport industry, basically. It's also used in reinforcements, so either as a matrix, and then you can add material around it. You can also use it as reinforcements of plates. And energy dissipation. So this is the link between the shoe and the car. So you can tune how much energy you can dissipate with your lattice. And then also you can do some really nice things in the bio industry, where you can create scaffolds and you can have cells that regenerate inside. So let's talk a bit about manufacturing. So obviously 3D printing. But I'm not going to talk about this. I'm going to talk about what we developed at Tetmet. So we have developed this robotic arm that's kind of tweaked to create these complex lattice structures. So basically what this means is our base material is just like regular rods. We have a laser, so we're able to weld the rods. And we also have some machine vision in there so that we can see if the welds are correctly done. So basically this is what is seen by one of the cameras around the head of the robot, and then we can really tell what's going on. The main advantages are what? Basically it's extremely cheap off-the-shelf equipment, so no really big tooling as you would have for stamping, simple source material, and also extremely low energy use compared to traditional 3D printing. The reason for this is we only spot weld a very short and a very low part of the rods. So indeed, we're not melting the whole thing. So it is very competitive in terms of carbon usage. So how it works, I'm going to try to, I think I have the same problem with my mouse. Okay, so this is the robot in action. So you can, sorry, this is not the robot in action. There it is. So you can see it welding, cutting, positioning, welding, cutting, positioning, filling gaps, and then kind of making this structure. The reason, this is relatively slow for the moment. We're in a lab environment, it's getting faster. This video is kind of old as well. But so we're getting there, and we're already faster than 3D printing. So a few examples that I have here as well. So this is what we're able to build. Basically, we can build any size. In terms of the size of the actual struts that compose the part, they are relatively big compared to 3D printing, but we still can have some really nice properties. So for instance, I can stand on this if I don't lose my balance, and it's perfectly strong. If you want to stand on it, I'll be over there at the end, and you can try. Another question we generally have is how do we interface with other parts of the assemblies, so we can weld on plates and we can have inserts. So the next question is, and it kind of circles back to the title of this talk, is how can we efficiently design lattices for our process called ASLM. And basically, we've developed a second part of the company, at least the tool. So it's called LDS. It's design plugins for CAD software. So we didn't want to build our own CAD software. We wanted to be in the environment of CAD instead of building something new. So when we started thinking about lattice design solution for ASLM, we identified a few key requirements. Obviously, we did our homework and we looked at stuff that you've seen today, but we always had to do that extra step because we needed to be manufacturable and we needed to have the right information that's sent to the robot. And so basically, we wanted something mechanically sound. What I mean is conformal. We can't have sticking out rods. Mechanically, it doesn't really make sense. Then the tool should be really easy to use for a CAD engineer, because we work for industries, so they have their standards, and it's not like what you would do for 3D printing. Third, we wanted it to be CAD-Integrated, because we didn't want to build a new tool, and we also wanted it to be ASLM informed. So basically what this means is all of the constraints of the robots are in there. We basically had a look at the current projects that we had, and we figured that most of the design requirements that we had came from traditional CAD designs. So what this means is we have artifacts from legacy ways of producing things, machining, turning, whatever. And so this kind of shaped how we designed LDS. We obviously wanted a fast and efficient CAD native solution so that people wouldn't be confused as to how it works in the workflow. And we wanted to keep the workflow very, very easy and reduce design friction. So if we look at a traditional workflow, it's I'm not teaching this to you guys, but so it's basically very simple operations: extrude, revolve, subtract, Boolean operations, nothing too fancy. And so this process is extremely familiar with CAD engineers and people who work in traditional industries. So for our tool to be adopted, we really went down that path so that it would be accessible for engineers. And basically what we do is we do an intermediate step. So instead of going from a sketch and doing traditional extrude and revolve, we mesh our sketch and then we extrude and revolve. So this step creates conformal lattices extremely efficiently because we inform in the design process, like where are the edges, where does it start, where does it stop, and it's very native and intuitive for a CAD engineer. So essentially what we've done, so this is the ribbon we have for Fusion 360. It's the first plugin that we've actually done and that's used by application engineering. So we have all of the normal things that you would find in a CAD software. So the traditional extrude, revolve, loft, whatever. But you also have some extra steps, such as generate nodes, generate cells, and I'm going to dive in a bit deeper into this. We also have some ASM-specific features, some convert functions for our robot and things like that. But that's maybe more useful for us than it would be if you were to download this from the Fusion Marketplace. So just a quick overview of what the features specific to creating lattice sketches do. So what you're able to do is you're able to create a selection of curves inside a geometry so that it's easier, and we have some algorithms to do some automatic cell generation. We also have, so yeah, these node generation things. So basically what you can do is you can tell what the minimum rod length you want, maximum, how many divisions and things like that. So it's parametric in a sense, but you do have to inform during the design what you want. You have some automatic generation of cells. So this is Delaunay, for instance. We have some others. If you want to do it by hand, you can, because that's the beauty of it. It's in Fusion, so it's native. So if you want to remove, I don't know, whatever line, you can remove it and add another one. And then we have these extrude functions where you can choose the distance, the offsets. It's basically exactly the same thing, but you get to choose a unit cell. And the same for revolve. So when you do curves, you have to be really careful because you have to approximate these with segments, but you don't want them to be too close. So you have to really think about how you're going to approximate your geometry. So this is one example where you can have a 6-step revolve or a 12-step revolve, but this is a revolution. There's also a loft option, and then you can do some really nice things. For instance, when you do a design, sometimes you have some things that you really want to tweak by hand, and this is possible by all of these features. So you can create some nodes. You can move them around like a sketch if it's not constrained. And then you can fix your geometry and merge different extrudes or revolves that you've done. So this is the difficult step. I don't know, the people from Carbon were saying that it's extremely difficult to connect them to a surface, but it's true. It's extremely difficult. So, but we do have a way of doing it. And then we can also fix some geometries, like for instance, if for some reason a node is too far off, we can connect it to its neighbors. And so, yeah, this is about everything I have to say about Fusion 360 and what we've done. The only thing I want to add is we have a really nice LCA tool. So when you design, you know. And it's also a feature that's really widely used in the aerospace industry and automotive industry. So a quick GIF of basically an airplane seat leg. This is really one of the first things that we designed, but it's just to show you that it's easy and we can do some nice things, and to show you that it's not just cubes and circles and stuff like that. This is an actual part that we were asked to do. Basically, you have the sketch, and we had to separate the sketch into different parts because they're not all the same thickness. And for it to be lightweight, because a lot of people do implicit geometries so that it's lightweight and it's easier to do. We can't really do this in Fusion, but we do have some workarounds. So we work with STLs, and then we can convert it, and then we can add some features. And here are some of the things that we designed. So this is why it's a bit different to your traditional lattice generation software that you can do. For instance, not to name them again, but in NTOP. Yeah, so basically this was a drone project that we did for the French air show that happens every 2 years, so this was this year. And then we had some really funky looking bracket thing that we were required to do, and what they wanted to do is like cheap and toolless. So this is why our solution was useful. And this is a connector, but what's really nice is because it's CAD integrated, you can already add some features that exist, or you can extend, and then you can machine stuff and use like the traditional mechanical engineering workflow. So as a conclusion, so LDS is CAD native, and it's a really pragmatic way of designing lattice parts. Nothing too funky for the moment, but we needed something that was robust and useful for us, so this is why we made it. And the next steps would be maybe going for some kind of optimization, but lattice optimization problems are really difficult. It's a whole field in academia. There are a lot of optimization functions that you can use. So maybe if it's user-informed, it's a bit easier to solve. And so that's why we haven't really gone the way of, like, we push a button, we generate a lattice. We want it to be user-informed and have the hard questions answered by someone who actually knows what they're doing. So yeah, this is it for me. So thank you for your attention. So obviously no questions, but if you do want to stand on the stuff and ask some questions about mechanical engineering and how we do things, because this is only just scratching the surface of what we do at Tetmet, we'd be really happy to have a chat. So yeah, thanks.
To see the full recording of this and previous presentations, as well as information about future CDFAM events, visit cdfam.com.